So in order to know whether or not you have a relative maximum or relative minimum, or maybe neither of those two situations, we have what's called the first derivative test. So the title tells you what you're doing. You're using the derivative to test what's happening at a critical point. And there's three basic conditions that can happen. One, the derivative changes its sign from positive to negative. Now remember, that means that the function is increasing, going up, because the derivative is positive. Then, after the critical point, the derivative is negative, so the function is decreasing. So if a function is going up, then turns around and starts going down, then you have a peak or a maximum, a relative maximum. On the other hand, in the opposite direction, if the derivative goes from negative to positive, that means the function goes from decreasing to increasing. It's going down, then it's going up, then that is a relative minimum point. But there's a third possibility, and that is that the sign does not change. And if that's the case, then at that particular point, you have neither a maximum nor a minimum. So this goes back to the little cautionary note that I gave you a couple of slides ago that said, usually the critical point acts as a place where the derivative changes sign. But that's not always the case. So here's a perfect example of what that might look like. Here's a graph of the function y equals x to the 3. So when I look at that picture, this is what it looks like. Now, focus your attention at x equals 0. The graph of this function comes from the equation y equals x cubed. So, when x is equal to 0, y is equal to 0. So it goes to the origin. The derivative of x cubed is 3x squared. So if the derivative is 3x squared, then the value of the derivative at 0, so 3 times 0 squared would also be 0. So notice if the value of the derivative at 0 is 0, then at that particular point, the slope of the tangent line must be 0. And that's exactly what you'll see here if you think about it. If you were to draw a tangent line at x equals 0 at the origin, you'd get a perfectly flat line. And what that's telling you here is that at that one point on the graph, when x is 0, this picture, this graph, levels off so that it's nice and smooth and nice and flat. But look to the left of x equals 0. At every point to the left of x equals 0, all of the tangent lines have positive slope. So they're very positive on the far left. They become less and less positive until they reach a 0 slope at x equals 0. And then, after x equals 0 to the right, they don't become negative. They go back to being positive. So what you see on the left is a bunch of positive signs for the derivative, then a bunch of more positive signs on the right, so you're not seeing a sign change happen. The function is increasing. For one moment it levels off, and then it continues to increase after that point. So this is not a maximum, it's not a minimum, it is in fact what we call an inflection point. It's where the graph is changing its inflection. So we cannot assume that a critical point will always cause or will always correspond to a change in the derivative from positive to negative or negative to positive. You could see positive to positive, or in other situations, negative to negative. So the sign must change to have either a max or a min. So let's keep that in mind. So let's take a look at a very simple example of how we could apply the first derivative test to a function. We're going to use a simple quadratic function. So if you remember the graphs of parabolas, which correspond to quadratic functions, you might remember that the leading coefficient on the x squared term, the number in front of the x squared, tells you about whether or not the parabola opens up or opens down. So if the number in front of x squared is negative, then it opens downward. If the number in front of x squared is positive, it opens upwards. So in this case, the number in front of x squared is, by implication, a positive 1. So the a value, we say, is positive 1. Positive, therefore, this opens up. Now, the question says, find the minimum or the maximum of this function. So we already know that since the parabola is opening upwards, that there's a minimum there. But let's go ahead, we'll keep that in the back of our mind. Let's pretend that we don't know what the graph of this function looks like. And so we're going to find the minimum or the maximum of this function. Now remember, minimums and maximums, relative maximums, occur at critical points. And critical points occur when a derivative is equal to 0. So the first thing we do is we ask ourselves, what is the general derivative of this function? And so that's our first step. So we start by taking the derivative, the general derivative, in this case from the power rule in topic 4. We bring the power 2 in front. 2 times 1 gives me 2. We keep the variable x. We reduce the power by exactly 1. So this is 2x to the 1. From topic 4, we also found that if you have a linear term or a linear piece of your function, then the derivative is equal to the slope of that line. So negative 8x is a linear term. The slope of that term is negative 8. And finally, the slope of a constant term, like positive 3 here, is 0. So this is the general derivative. And so we look for critical points, which means we want to know when this expression is equal to 0. So literally, we set the expression equal to 0, and then we solve. And whatever value or values of x, or whatever independent variable we have that we get, that tells me what all of my critical points would be. So in this case, this is easy. This is a linear equation. We can solve that by adding 8 to both sides of the equation, and then isolate x further, and finally by dividing both sides by 2. So that tells me that x equals 4 is a critical point of this function. In fact, because it's the only value where the derivative is equal to 0, it is the only critical point that this function has. So if you think about the graph here of a parabola, there's only one turning point, one minimum on that parabola. This is where it occurs. Now, let's go back to pretending that we don't know whether or not we have a minimum or a maximum at that point, x equals 4. We're going to use the first derivative test to determine what's happening at that critical point. Now remember, the first derivative test asks you to look at how the derivative may or may not change its sign. So first thing to notice about this process is that we are looking at what's going on with the derivative. That's why we call it the first derivative test. So this little number line here serves as a measurement of values of the derivative. And what we do with this number line is we break it up into regions, and those regions are marked off where you have a critical point. So we only have one here, so we're going to mark the critical point x equals 4, and this creates 2 regions. So think back to the graph I showed you earlier in an earlier slide where I marked off where there was a maximum and there was a minimum, and we had 3 regions there. In this situation, we only have 2 regions because there's only one critical point. Now, what we do is we look at some arbitrary value of x in each region. So let's look at the region on the left here. We pick any point to the left of x equals 4, and we plug that into the derivative so that we can see what its sign is. So I'm going to pick x equals 0 because 0 is an easy number to plug into expressions. So the derivative, remember, is 2x minus 8. So f primed at 0 is 2 times 0 minus 8, which of course is negative 8. So I start by picking x equals 0. I plug it into the derivative, and then I get a final result. And then I take that result and I plot it, so to speak, on the derivative line down below. So I'm going to put a bunch of negative signs, and that tells me all the derivatives in that region are negative, and therefore I know the function is always decreasing in that region. So to the left of x equals 4, that function is coming down. So that's region 1. Now we move to the next region, region 2 on the right. We will pick x equals 5, let's say, anything to the right of 4. So we choose our x value. Next, we plug that into the derivative. So f prime of 5 is equal to 2 times 5 minus 8. And then we do the calculations till we get a value of 10 minus 8, which is 2. So that value is positive. And so then we know that in that region, all of the derivative values, no matter what x you pick, will be positive, and therefore the function is increasing in that region. Now, a couple of things to notice. What's happening at x equals 4? What's the value of the derivative there? Well, if you thought to yourself or you said out loud the derivative is 0, you're right, exactly. That's the definition of the critical point. At x equals 4, the value of the derivative is 0. So that tells me then that the function is changing its derivative sign from negative to positive. That means the function is decreasing and then increasing, or it's going down then up, and so this is a relative minimum. And there's your parabola. One more thing. Think about this question. Is there any way that this function could change its derivative sign, let's say, way off to the right? Let's say out at x equals 3 billion. Is there some chance that the derivative sign could change from positive back to negative? The answer is no. And that's because we found one and only one critical point. So therefore, there's only one point where you could see a potential sign change. This is it right here, x equals 4. There are no other points for this function where that could happen, so you know there's no other place where the graph could either have a max or a min or possibly what we called an inflection point. Let's now take a look at an example that's a little bit more complicated. The previous example was a pretty straightforward parabola. We already know what that looks like. Here's a situation where we have a function that is not a quadratic. Its highest power is no longer 2, so it's not a quadratic by definition. It's what we call a third degree or a cubic function. So the shape of this is probably not too familiar to most people. And it's very difficult to predict what's going to happen. So let's apply the first derivative rule so that we can find and classify all of the critical points that may exist for this function. So remember, the first point to determining and classifying critical points is to find the value of the derivative, or actually find the general derivative and set it equal to 0. So the general derivative here comes from topic 4. The derivative here would be 3x squared minus 12 times x minus 15. And so we take that derivative, we set it equal to 0. Now, at this point, it's an exercise in algebra. The calculus part is done. Taking the derivative is using calculus. The rest of it is using algebra to solve this equation and to find out what values of x give you 0. So there are two basic ways to solve a quadratic. Once it's equal to 0, which in this case it is, you can either apply the quadratic formula or you can factor the expression. So for those of you who prefer and like the quadratic formula, you can do that here with a equals 3, b equals negative 12, and c equals negative 15. And as long as you do the arithmetic correctly, you'll get to the correct critical point or points. But I've chosen this one so that we can just use factoring. So when you factor, what we typically do is we look for anything that all of the terms have in common first. So what we call the greatest common factor could be a number, or it could be a variable, or it could be both. So anything that all terms have in common, we factor out first. So in this case, all three terms have a 3 in common, so that's part of the GCF, the greatest common factor. And we could look and see if they all have, like for example, an x in common, but you can see that only 2 of the 3 terms have an x. So x can't be part of the greatest common factor. In other situations, especially on homework, you may have to factor out an x as well, or even maybe even a higher power of x. In this case, the GCF is just a 3. So we pull that out, leaving x squared minus 4x minus 5 in the parentheses. Now, this trinomial, this quadratic trinomial, allows us to factor further. So going back to factoring techniques, we can break that trinomial, 3-term polynomial, into 2 binomials in this way. The first factor is x minus 5, and the second factor is x plus 1. So now we have a completely factored expression on the left, and it's equal to 0. Now remember, the only way that you multiply 2 or more things together and get 0 for the result is if one or more of those factors is equal to 0. So to solve this, we take each of the 3 factors that we've produced and we set each one equal to 0. So it looks like this. Either 3 is equal to 0, or x minus 5 is equal to 0, or x plus 1 is equal to 0. And this leads to these 3 scenarios. Either 3 is 0, either x is 5, or either x is equal to negative 1. Maybe all of them are true, maybe none of them are true, but the point is these are the 3 possibilities. Now, of course, you look at 3 equals 0, and that's a completely false statement. So we rule that out. That doesn't give us a meaningful solution. So since 3 is not equal to 0, that produces nothing meaningful for us. But the other 2 situations obviously do. Either x is equal to 5 or x is equal to negative 1. And if either of those 2 things is true, let's say x equals 5, then x minus 5 becomes 5 minus 5, so 0 times whatever is going to give me 0, which is what I'm looking for. So therefore, what we have here are 2 critical points. X is equal to 5 and x is equal to negative 1. Those are the only 2 points on the function g. Those are the only 2 points on the function g where you could have either a max or a min or potentially an inflection point. So we have to mark those off on the number line and then apply the first derivative test. So let's go ahead and do that next. Okay, so let's get this set up. Notice at the top we have the derivative written in 2 different forms. We have the 3x squared minus 12x minus 15 form, the polynomial form, and then we have the factored form. And the reason we have both is because, remember, what we're going to be doing here is substituting values of x into the derivative. So we want to think about what's the easiest way to quickly substitute values of x into a derivative. And the derivative, depending on what form it's written, can help us out or maybe hinder us. Next thing to notice, once again, is that we are measuring values of the derivative of g primed. So on the horizontal line here, we are basically testing different values of derivatives. And then you can see the 2 dotted lines each one corresponding to a critical point, the first one at -1, the second one at 5, creating, once again, 3 distinct regions. So we will move from left to right, and we will test a value of x in each region. Now, it does not matter what value you pick, so you can pick anything that might be convenient. So on the left, we're going to choose x equals -2. Now, notice what I've done. I have plugged or substituted -2 into the factored form of the expression. So go back up to the top and look at the factored form of the expression on the far right. If I plug -2 into the parentheses where you see x minus 5, you get -2 minus 5, which is -7, and then -2 plus 1 gives me -1. So now g primed is equal to 3 times -7 times -1. And if you actually multiply that out, you get positive 21. The actual numerical value is not as important as the sign. The sign here is greater than 0, therefore the derivative is positive. So remember, if the derivative is positive, then the original function g is doing what? Of course, yes, it is increasing. So we can mark that as an increasing function in that region. We next move to region number 2, in the middle. Any value between -1 and positive 5 is okay, because all of the signs for all of the derivatives in that region are all going to match. So we pick anything that's convenient. I usually pick 0 if possible. So if I plug 0 into this, I get the 3 on the outside, which of course is positive. In the middle, 0 minus 5 is negative. And then on the right, 0 plus 1 is positive. So I have 3 times a negative number times a positive number that will result in a negative value. It's less than 0. So the derivative in that region is negative, and therefore the function is decreasing in that region. Now remember, we don't automatically assume that because we got positive signs on the left that it automatically switches over to a negative there in the middle. We saw an example where it could be positive, level off for a quick moment, and then stay positive. So we always want to do this test if we are not sure about what's happening. And then finally we have that third region on the far right. Any value will do. I can pick x equals 10, for example, and when I plug 10 into the factored form of the derivative, I get 3 times in the middle. 10 minus 5 is a positive number, and on the end, 10 plus 1 is also positive. So 3, which is positive, times 2 more positive numbers gives you a result that is positive, and therefore in that final region on the right side, the function g is increasing. And so now we can sort of picture what's going on with the original function g. Keep in mind, g primed is telling me the signs of the derivative. At x equals -1, the sign changes from increasing to decreasing, positive to negative derivative. So that tells me I have a relative maximum there. It's going up, then it's going down. At x equals 5, it's going down, and then it's going up. And so you have a relative minimum. So if you were to sketch this curve, it'd look a little bit like this. The function is increasing till -1, then it decreases until you get to x equals 5, and then increases from that point forward. So this is the general shape of the curve. It doesn't tell me how high up or how low the y values are, but those wouldn't be hard to find because we have g. Remember, y is equal to g of x, the original function. So if I want to know how high or how low g actually gets, all I have to do is plug -1 and +5 into the original function, and then I'll get all the y values. But remember, the point of this is to find the critical points and classify them. We have 2, one at -1, which is a relative maximum, and one at +5, which is a relative minimum. So here's a little test of whether or not you sort of have these ideas.